Hello. We're now going to look at the concept of linear regression. Linear regression is a method of relating a continuous response variable to a continuous predictor variable. Now, if there is a relationship between the response and the predictor, of course that doesn't necessarily mean that there's a causal relationship, i.e. that X causes Y. The approach of linear regression is widely used because we often ask questions about relating one continuous variable to another. For example, we could ask, do seabirds from larger colonies take longer to find food? And this is what we'll be looking at in a later example. Here's the trip duration against the square root of the colony size. And we're simply asking, as the colonies get bigger, does the trip duration also tend to get bigger? We could ask, for example, do brightly coloured birds tend to have more parasites? Or does the concentration of cesium vary with sediment depth? Linear regression describes relationships between continuous variables, but also tests for evidence of a linear relationship of a given slope, particularly of a zero slope. Can we reject the null hypothesis that at population level there is no relationship between, for example, trip duration and root colony size? The approach was popularized by Francis Galton in 1889, who was very interested in heredity, particularly instances such as tall parents giving rise to offspring who are tall but not quite as tall as themselves, a phenomenon known as regression to mediocrity. But the overall approach was further developed by Pearson and Fisher. How does the standard Model 1 linear regression work? Well, first of all, it estimates parameters describing the relationship, and because it's linear regression, we need only estimate a gradient and intercept. And secondly, it conducts hypothesis tests based on the overall variability in the data and how the response variable y varies with the predictor variable x. In particular, it asks, can we reject the null hypothesis that at population level, the true gradient relating y to x is zero? So, how does model regression work? Well, at population level, we assume that the world is rather linear in that we have a population level intercept and a population level slope beta, and we have variability around that overall model. And that variability has a mean of zero, but fixed variance for whatever level of the predictor we are considering. Now, it's important to note that that error, although it is called error, is really an inadequacy of the model in explaining all of the variability in the data, rather than an inadequacy of the data or even the experimenter. But in the real world, we rarely deal with full populations, and instead we sample from these populations. So let's imagine we've taken a sample and the data are relatively limited. So we have a relationship between y and x, and we want to infer things about the population from which that sample was taken. Now imagine we take a line of least squares best fit through that sample. That's a line which minimizes the sums of squares of deviations of points to the line. And let that line be called a straight line with coefficients a and b to distinguish it from the population level characteristics alpha and beta. Well, there's some good news. If we define the line of best fit in terms of one which minimizes sums of squares of deviations, then because we're prepared to assume normally distributed error, it turns out that A and B are unbiased estimates of the coefficients alpha and beta, which is great. Something else you should know. So imagine this is the population, and one time we collect some sample data and estimate the line of best fit through A and B, and of course that's an unbiased estimator of alpha and beta. But next time we do it, we almost certainly will not get exactly the same estimates of alpha and beta. Let's call those A dash and B dash. It turns out that statistically we can estimate the expected standard deviation of our values A and B, and they're known as the standard errors. That is, we can put a degree of uncertainty into our estimates of A and B based on the strength of the relationship and the variability in the data themselves. Now, Model 1 regression assumes that the predictor is measured exactly. So the line of best fit is one, as I've suggested earlier, is defined by minimizing sums of squares of deviations of observations to that fitted line. So we're going this way rather than some combination of vertical and horizontal. Likewise here in this relationship between volume of a tree and its height, we're minimizing the sums of squares of the vertical deviations. Now, it's typically most appropriate when that predictor is controlled exactly or measured exactly. But in cases where it's not, you can still get away with conducting Model 1 regression. That's what most people do, so long as we're relatively careful in our interpretation with regard to what is measured. How does Model 1 regression work? Well, the first thing is that it creates, in one way of seeing the regression, an overarching analysis of variance, and I just want to introduce this to you. The first is an index of the overall variability in the data. This is the total sums of squares of points around the overall grand mean. So there's the grand mean response, and we're simply working out a total sum of squares, just as we did with the analysis of variance. So that's one measure of the variability in our data. But there are other measures. Remember, we fitted a line of best fit through our data, so we can work out the sum of the squared residuals around that fitted model. And of course, here I'm using the fitted model value as y cap because it can change with the value of x. So for each case, we've got a distance between the point and that fitted model. And of course, if the model fits very well, we would expect that error sum of squares to be relatively low. The final thing we can think about is the deviation of that fitted line from the grand mean. So for each and every data point we have, what's the sum of squares of the fitted model to that overall grand mean? And that's called the regression sums of squares. So it's the sum of the squares of the difference between the grand mean and the predicted value for that given data point. So we've partitioned variability through these sums of squares just as we would in a normal analysis of variance, and it turns out they are neatly additive. The total variability in the data, as expressed in terms of sums of squares, is equal to the variability explained by the regression, and the variability is explained by error around that regression, i.e. not explained by that regression. So that's really neat. It turns out that simply knowing these sums of squares allows us to calculate something called the R-squared statistic. This is the proportion of the variability in our data as expressed with sums of squares that is explained by the line that's been fitted. So R-squared is a nice measure of the degree to which the model explains the variability in our data. But there's something else too. These sums of squares can be used to calculate two separate estimates of the variance in the underlying data. Now it turns out that if the null hypothesis of there being no relationship between the response and the predictor at population level is true, then these two estimates of the variance will estimate the same thing. So for this we need to know the degrees of freedom behind each of these sums of squares, because a variance is a sum of square divided by an appropriate denominator, which is the degree of freedom. This is the technical part. But in essence what we do is we calculate two estimates of the variance, one based on the regression, one based on the error, and if the regression truly, if the relationship between y and x is truly flat at population level, then they should be estimating pretty much the same thing, and so their ratio should follow an F distribution. What other assumptions do we make behind the Model 1 regression? Well, Model 1 regressions are examples of general linear models, and so you will become increasingly familiar with these. For any value of x, any value of that predictor, the error distribution around y is assumed to be normal, as I've depicted here. So most are close to the line, a few are far away this way, and a few are far away that way. We're also assuming that the variance of the error distribution is the same for all values of x. And finally, we're assuming that the model is correct in that broadly at population level, y is indeed linearly related to x. Whether it's a flat line or not, we need to assume linearity in this particular relationship. And that's an important reason for plotting your graphs first before fitting an overarching model.